So welcome back. My name is Jens-Carsten Hansen. I'm the chairman from Technical University of Denmark. I'm the chairman of this first topic session on wind resources. That's certainly a wind power without borders topic. And although wind power and wind resources without borders sounds like it could be uniform, it's certainly not. It's a highly varying resource of wind we have across geographic areas and in time as well. So it's a highly challenging topic, and a topic with great importance because it's fundamental information you need to be able to plan, to be able to make policies and decision making, and to be able to develop projects. And it's important for investors, for country, for taxpayers, for everybody. And it's a fundamental information. As I said, we are pleased to have 4 speakers with excellent and interesting address of this topic and the science in this. So I'm looking forward to listening to these presentations. And the first one, I'm by the way referring you, in the interest of time, the bios to the material you got. You will be able to read about the presenters in that. And our first presenter is David Pullen on novel statistical validation of long-term consistency of reanalysis models in South Africa. So looking very much forward. Please take it away. I will waive 3 minutes and 1 minute signs over here when you're getting close to your 15 minutes. And then we'll have questions from the floor after. So please go ahead, David.
So I'm David Pullinger. I'm the technical lead of the Energy Resource Services team at Lloyd Register. I do wind resource assessments, basically. So anything wind resource related, that's my thing. So measurement campaigns, site finding, all the way through to operational performance of wind farms. Okay, so Lloyd Register, I'm not going to talk about who we are, who I work for, but if you've got any questions, come up and talk to me during one of the breaks. And what are we going to do? Today we're going to talk about those little onshore turbines you can see. Okay, right, so we've done the introductions part. So next I'm just going to give you a little bit of context, then the motivation, methodology, results and conclusions. What I'd hopefully like you to take away from this presentation is, firstly, an understanding of this statistical technique, how it works in a nice, hopefully well-explained format, and also how well does it actually perform at detecting inconsistencies in reanalysis data. Okay, so just a little bit of context there. In order to value a project, we need to know how much revenue it's going to generate, which is ultimately how many megawatt hours, gigawatt hours, hopefully, your wind farm's going to produce. So to do this, we follow, we perform a wind resource or energy yield assessment. And this typically has, we break it down into 5 steps. So firstly, measurements. We'll take measurements short term for a period of 1 to 5 years on site using a meteorological mast. Then we want to perform a long-term assessment to understand what are the wind conditions likely to be over the 20-year or 25-year lifetime of the project. Once we've done that, we've got a series of point measurements across your site, and then we need to create a wind flow model. So this is a model, a sort of 3D space across your site where we're going to place the wind turbines. Within this model that we've created, we're then going to place turbines, assess their performance, how many megawatt hours they're going to produce, and understand the interactions between those turbines. And then finally, perform a loss and uncertainty assessment. So losses are things like electrical losses, or an account for downtime, say due to grid or turbine downtime for maintenance. And the last part is uncertainty, which takes into account how good all the inputs, all the models, everything we've done to the data, all the way from measurements all the way through, everything we do has an uncertainty. And so at the end of that, you come out with a probability distribution of these are the energy yields that we think you're going to produce. So that's what this research sits within, sort of wind resource, but I'm going to be focusing in on that long-term assessment box. So the question arises, what do you need for long-term assessment? Well, what we use to predict the future wind speeds at a project is the historic. We use an old long-term record. So what do we use for that? So there's two sources. I'm going to sort of categorize them as. We've got ground stations, so typical measurements made using an anemometer. You can see a mast there on the left. And then the second is reanalysis data sets. So for ground stations themselves, we want to understand the consistency of these data points, of the data it produces. Consistency is important because what we're looking for is representative wind. So we want to know what the conditions are going to be like in the future going forwards. And so any artificial change in the historic data that we've used will mean that our future predictions aren't going to be representative and or are likely to contain a bias. So ground stations are a sort of traditional approach that people use. They're easy to a certain extent to understand. So it's an anemometer mounted on a mast with a wind vane, and hopefully they have good metadata, which is station logs of things like sensor changes, mast movements, changes in exposure. So I've brought two examples here. So on the left, you've got a South African Weather Service mast. You can see that this is somewhat bowed, so it's curved, and I would suggest that when it was initially erected, it was straight, it was vertical, and so over time this has slowly started to curve, which means that the wind speed readings from this sensor will have changed over time, as instead of measuring the horizontal wind, they're now measuring something off at a few degrees. So this is an example of a poor ground station. And then on the right, those are penguins, obviously. I don't know why I've got two pictures of penguins in a presentation on wind. It just so happened to turn out like that. But at Cape St Francis, they've got a reference station, and next to that station, a few years ago, they built a penguin enclosure, a one-storey building, the penguin sanctuary there, that's about 30 metres away from the mast. And again, that one-storey building has quite a big impact on the wind flow that the mast next to it is experiencing. So that's ground stations, and they're easy to assess, but they often have their problems. The alternative that I mentioned earlier was reanalysis data sets. These are based on global climate models, and as the name suggests, they're great because they're global. They have very long historic periods, over 30 years, and they take readings from millions of readings from satellites, ground stations, weather balloons, all sorts of readings, take those in and produce these global models. And so they are great because they have a very long record and they're everywhere, but the disadvantage is that we can't perform the same sort of validation on them as we would with a ground station. We don't have time or the will to go through those millions of data points to ensure that they're consistent. So what we need is to look at the output of the model instead of the inputs and validate the output of those models and their consistency. And consistency, I keep banging on about this, but it's important because if it's inconsistent, your future wind isn't going to be represented well within your models, which will lead to a bias in your energy estimation. So then your wind farm, when it's built, will not produce what you've predicted. Hopefully this will move on to the next slide at some point. Not quite sure where I'm supposed to be pointing it. Can we move to the next slide, please? So anyway, I'll just kind of carry on. But so when people are assessing consistency, well, that was quick. When people are assessing the consistency of their data sets, there we go. That's spoiled all the next bit. Cool, that one, perfect. Typically, people use quite subjective methods. People look at graphs, and they don't have an objective measure, which is what this statistical technique, change point analysis, that I'm going to introduce in a minute, does. So for the studies we're looking at, we need examples of consistent and inconsistent data. So we've got that from 21 masts, that's 12 South African Weather Service masts, and 9 Wind Atlas of South Africa masts. And they're spread across the country, and then each of those 21 masts has been paired with a reanalysis data set, a MERA2 node and an ERA interim node. And so we've got examples of consistent and inconsistent data that we can test this statistical technique on. So next I'm just going to hopefully run through briefly and give you an understanding of of how this statistical technique, which is called change point analysis, works. There we go. Right. Okay, so if you want equations and references, there's a reference slide at the end of here, but the equations are in the paper, which you'll all be able to access after this, but I'm just going to run through it quickly and visually. So what we've got here is the grey dashed line, the lower one, is a wind time series. So that's wind speed over 12 months. And then what I've done to create an inconsistent time series is from time step 6 onwards, I've just added 2 meters per second to create this artificial inconsistency. And the way change point works is by applying a cumulative sum. So this goes through from time step 1 or 0 through and calculates the difference between that data point at that time and the average of all the data points in that time series. So that means that if the wind speed is below the long-term average, then you get a negative value, and if it's above, you get a positive value. And then it sums them up cumulatively as you go through. And you can see that on the next slide, hopefully. Can we move to the next one? I see some movement. Oh, there we go, right. So this is the cumulative sum. So you can see on the left, for that consistent plot, it wibbles around 0. And on the right, you've got a series of negative points, which correspond to those lower than average wind speeds, and then a change, which causing it to come back up again. So you've got those 2 different shapes. But those shapes in themselves don't tell us too much. What we want to know is how likely it was that this particular pattern occurred. So, for example, on the right, that you got 6 below average wind speed months and then 6 above average wind speed months. And so we do this by bootstrapping, so taking the time series, jumbling up the order of each of the readings and generating these patterns effectively through time. And you can see that in these nice blue dots. These are individual bootstraps. And I've displayed 20 here, but typically we'd run sort of 10,000. And the scales are now the same. So you can see you've got this sort of cloud of blue possible combinations. And on the left, the cloud is quite narrow because there's less variability in the data. And on the right, there is more noise, there's more scatter between them. But you can also see, hopefully, on the left, the orange line still sits in the middle of the cloud. And on the right, you can see at sort of time step 5 and 6, it's sticking out, it's on the edge of this cloud. There we go. So what we can then do is for each time step, you can take a sort of vertical slice at time and say, how probable is it that we've ended up with this particular cumulative sum? I can see a card being prepared to be waved. So this is the probability distribution of those cumulative sum values, readings, and you can see here that the orange is an outlier. So it's quite improbable that will have occurred. And then hopefully the next slide will show you what it's like for a consistent data set where it's somewhere sort of in the middle. Okay, so we did that. We ran through it for each of those 21 masts, 21 mirror nodes, 21 era interim nodes, and we got these results. So false in this example is where the data is consistent, and true is where it's inconsistent. So those two white boxes, the 75 and the 27, where it's actually predicted the outcome correctly. And of particular interest is that, so those 75 and 27, that's 87% of the time. And those, what is of particular interest is that 4 number in the bottom left. This is what we're trying to avoid, in particular, where there is an inconsistency, so it's actually inconsistent, but it hasn't been picked up within the change point technique. But that only occurs 3% of the time, so I think that's quite a good result, good turnout. Hopefully, right, there we go. Okay, so conclusions from it. So the first finding is that reanalysis sources contain inconsistencies. I've seen lots of reports, sort of academic ones, and from consultants like myself, where people don't even consider that reanalysis sources could be inconsistent for the purposes of wind energy. And so what we'd recommend is that all data sets are checked thoroughly for inconsistency, which will eliminate errors in future analysis. And then, we've gone slightly too far, but anyway, the second finding is that change point's pretty good. It's right 87% of the time, but probably more importantly for the work that I do in particular is that it has a 3% false negative rate, which is what we're trying to avoid. So the action from this sort of finding is we think people should apply change point. It's an objective method. It's a number that people can compare, but you still need to be careful with the results. It's not the answer to everybody's problems in this particular niche field, but it's a useful tool in that toolbox. And the final finding, which so this has more information in the paper about the other work, but that reanalysis sources are as good as ground stations for long-term wind resource assessment if you're using them as a reference data source and they're both consistent. So the background to this is when we initially started using reanalysis data in our bankable assessments, we applied an uncertainty, an additional penalty to it because we weren't sure that it was any good. But our research in other markets across the globe has shown that this isn't true, and this work has done it for South Africa and kind of demonstrated that you don't need to add that extra penalty here. And then, so last bit, there we go. Who does this work actually impact on, those conclusions? Well, it impacts on people like me, wind analysts, academics, researchers, students who are dealing with long-term wind data. It impacts on developers, owners, operators, investors in wind projects, as it will hopefully benefit their projects in providing more robust assessments, and then also it will help system planners, grid operators, people looking at larger systems understand the sort of variability in their resource in particular. And then finally, I guess further work, we're looking into this in other markets, other regions. We're constantly expanding it and sort of tweaking the models themselves and also applying it live to wind data. There's some references which obviously aren't of interest now, but when you download the papers or presentations later, you can access them. And so that is the end of the presentation. Yeah, thank you very much.
Investors are interested, obviously, in the quantity of wind speed that's likely to happen so they can understand the quantity of wind power. Are they interested in anything else about the wind speed, like the forecastability And I ask that question because some wind power owners have to forecast their wind speed and they're financially punished for going above or below what they say they're going to output, or the consistency of wind speed, or anything else like that.
Yep. So yeah, you're absolutely right. There's one thing making a sort of judgment pre-build that it's going to produce over the long term, 20 years, this much, but they care about. So for forecasting, for example, there are countries sort of like Ireland, for example, has that sort of bid system in place, and this is a tool that you can run live as well. So instead of analysing the whole data set, you can add one data point at a time, rerun the analysis, and check for those consistencies. Forecasting is not my field, not because it's very complicated, but it is very complicated. We use the sort of historic things to produce those, produce our long-term forecasts. An average over 20 years is much more straightforward than saying what the wind speed is going to be tomorrow or next month. But it's the beauty of the tool itself is it can be used for both looking at big old data sets or running it live and getting those flags. Obviously it requires a bit of tuning and a bit of learning of the data set to know where to set those thresholds. Cool, thank you.
Any more? Andrea over here.
So perhaps a more practical question. So if you run your consistency through one of the reanalyses and you find it's probably flag you a particular period that something appears to go wrong. So in practice, what do? You still need some source for long-term correction. Right?
So it depends on when that occurs. So you might have, you start off with a 30-year data set, for example, and then it flags a data set in the middle. Then we cut it, remove that inconsistency where possible. Obviously, so you're ever reducing the amount of data you can use, and that's increasing the uncertainty in your approach. But typically we'd run a lot of different models, try a lot of different data sets. So practically we want something that's consistent, so you might end up cutting it and cutting it and cutting it until there's no benefit or there is no long-term reference longer than your actual site data, which is more uncertain. So that's what we do.
Okay. Another question, I don't know, do you find that in the MERA 2 or the ERA interim you find more inconsistencies in one or another?
The ERA interim has a lot more inconsistencies that we found. So MERA 2 there's a few, very few, but there are still some, but ERA interim there's a lot more. But when they, if you remove all the inconsistent data or data points, then the ERA interim outperforms slightly in terms of actual correlation, which was surprising.
Interesting. Thank you.
Thanks.
A final question? Yes? In the middle, down here.
Hello. Thank you. Yes, have you, this is Greg Poulos from ArcVera. Have you investigated how the inconsistency results that you've presented change based on the how far back you look in time in the reanalysis data sets? The reason I'm asking is because the data content available for periods prior to about the year 2000 is much less, especially with respect to satellite data.
Yep.
So what have you found there if you've investigated that?
So interestingly, there isn't an obvious point where these inconsistencies are flagged. It's not as if they all happen at a certain time. There's, depending on the reanalysis source you're using, they have quite big step changes in the input. So in our assessments that we perform on a practical level, we typically only use back to the start of 2003, 2002 as our long-term period, because that's 15 years, which is pretty good. But we haven't, the change point technique in this study hasn't actually sort of supported that finding. The inconsistencies are appear to be fairly random. Obviously, if we ran that on the global data set, maybe we'd pick up more trends, which is an interesting area of future work.
Okay, the last one. Yeah, very last one. Quick one.
David, I would like to ask, there is a project for device implementation of this novel statistic validation of long-term consistency of reanalyzed model. There is a project to make all of this modelization in one device to...
So it's we've just implemented it in Excel. It's a fairly... it's quite a simple technique, and so we've written the code. The sort of instructions on how to do it are open source, available on the internet, so anyone can take it, apply it to their data themselves, and then it's just the question of learning. So if you've got a different application that's not, for example, WindData, which has its own unique attributes, then you'd want to set different thresholds and maybe apply different parameters to it. But it's not a product as such. It's a tool that anyone can use, sort of open source.
Thank you very much, David. And let us give David another appreciation. Thank you.
Okay, so this is a tough one because, of course, codes are, especially comparing commercial codes, there's always the question of, what do you say about my code? Okay, this is not the goal here. The goal is to see where one could improve the input to such models and codes, and is there perhaps a way of combining the codes in order to build a better code. So the title of my presentation basically is benchmarking commercial codes you pay for, microscale modeling. That is probably involving the 800 meters, first 800 meters of the atmosphere, and see how the wind develop in this area, okay, with all environmental conditions considered. Okay, let me just check, hopefully. Oops. Okay, so the outline of this talk, basically giving an idea why we're doing this benchmarking, what is the benchmarking setup process we followed. I'll briefly touch on the pre-processing, solving, and post-processing for the codes chosen. Results and some conclusions, and a glimpse of future work. This is very much still a work in progress. Okay, so no results or conclusions here are final or complete. Okay, it's very much just but it's a very good start nonetheless. All right, so why are we doing benchmarking? Okay, and this is what you see here is two plots. Okay, the plots on your left-hand side top. This is a historical histogram of the annual energy productions of wind farms industry-wide up until 2011. Now you'll see that most of these wind farms yield only 91% of their predicted pre-construction energy yield. Okay. So why is this? Is it because of a mixture of old and new turbines? Is it modeling-based? Is it prediction-based? Is there perhaps assumptions that is not really accounted for or really well verified? Okay, these are all questions that the industry is still on a daily basis concerned with, and academia research. Okay, do a lot of research into this. So if you look at this bottom graph here, this is a smaller sample size by DNV, now Germanische DNV. So of course the results will look slightly better due to the smaller sample size, and I think this is also a newer up until 2016, so perhaps there's something to do with technology and technology improvement in coding, modeling, and wind turbines themselves. Okay, so end of the day you want to improve the accuracy of your energy production forecasts, okay, prediction prior to construction, okay. So my focus in this presentation is mostly on the microscale modeling. Where does the inaccuracies come in? Can one, by some means, minimize it? And if we minimize it, what's the implications? Okay. you need a battery here. Okay. So here we have a graph showing the profit over a lifetime of a wind project, the blue being the base case, and the orange line is base case plus 10% increase in energy production. So this if you can improve the accuracy of these models, microscale models, and yielding such a improvement in energy prediction, then you can end up with a 20 million euro profit gain. Okay, so it's very much important. Every percentage gain in accuracy counts. Okay, so our setup, we scanned and screened the available commercial codes. There's quite a lot of them. Some of them are older, some of them are new. The oldest code is mostly where all pretty much started is with WASP. We all know that. And then the newest one is open foam-based wind, which is OF Wind. It's the latest kit on the block. So we didn't have the budget or time to look at all of these codes. We only select two within the spectrum, a linear code and a nonlinear code. Okay. And like I mentioned, the goal was to compare the capability of these codes, but also expose the data shortages and how to correctly and what data to import and to make viable and accurate energy yield predictions. So we selected the best, one of the best, not the best, but a very good data set. That's the WASA data set. We selected a flat terrain site and then a complex site. The flat terrain site is slightly a couple of minutes south of Beaufort West. That is now, for this presentation, I'll call it WM07. And then the complex site is east of Rhodes. It's just south of the Drakensberg. So I will call it WM11. Here you can see the mast, 62-meter masts. All right, so the basis for comparison is to have a good quality, a high quality data set as input, reasonable terrain data, and then both codes should be compatible. The data format should be compatible in order to eliminate inaccuracies induced by data transformation between different codes. Comparison limitations, we did not include any real analyzed data. Okay, we only used measured data of one mast. Now that is problematic, of course. You need to actually include more masts, but for the time being, we start with one mast base comparison. And we only use a single turbine, okay, not to include wake effect modeling whatsoever. So the measures of comparison we use is a wind resource map, some wind profiles, and then the gross energy production estimate based on a fictitious 2 megawatt wind turbine. So just showing you the pre-process, we're going to run through the pre-processing steps. This is the terrain model, a 20 by 20 kilometer area with 5 meter vertical resolution. And you can see the flat site, the maximum difference in vertical height is 166 meters, and then the complex site is almost a kilometer. Oh yeah, just go back. The red dot here is the location of the placement of where the dummy wind turbine was placed. Okay, yeah. And then the land cover data, or data used to calculate the surface roughness that need to be included in the modeling. It was based on the 2014 CSR land cover data set. It has a spatial resolution of 30 meters. On the bottom you see the typical range of these roughness parameters calculated. Now the normal or flat terrain site has mostly barren land with some low scrub covering, and then the complex site is mostly grasslands. So we went for 0.06 for the barren land and 0.05 for the grasslands. Looking at the climatology, now again, WASA is there's some long-term data available, but we only stick with 2016 data. This data set includes wind direction, wind speeds at 5 levels, temperature gradients, relative humidity, and barometric pressure readings. Okay. The climate data here is for the normal flat terrain site, and you'll see it's mostly east-west wind direction, which is predominant, and then the wind speed is roughly, average year wind speed is 6.7 meters. Do you note there's a bit of a change in the Weibull fitting and the histogram? Okay, there's roughly 1% change in frequency there. So it's important to note this because it makes a difference if you use your Weibull instead of your histogram in your modeling. Okay. There's an additional source of error. Looking at the complex site, very strong direction, prevailing wind direction coming from west-northwest side. Slightly higher wind speeds, 7.9, and again there's a huge underestimation if you use the Weibull versus the histogram. So it's advisable always to use the histogram if possible, if it's available, of course. All right, now this is a tricky one, atmospheric stability. Okay. The atmospheric stability we calculated from the gradients, temperature gradients measured. Now these gradients are measured between 10 and 60 meters at each mast, one of the masts. Now there's 3 different classifications: as neutral, stable, and unstable. And the thing is, it's not a constant phenomenon. It's cyclic. It changes from day to day, hour to hour, season to season. Okay, and how do one, as a modeler, incorporate such a high variable phenomena, atmospheric phenomena? Okay, that's quite tricky. So we looked at the year, the gradient, temperature gradients measured over the year, and actually get a pointer. If you look at the plain and normal site, there's almost 50% of the time it's unstable, and probably it's almost half stable, unstable throughout the year. So what do one assume there? Do you want to go for stable? Do you go one with unstable? Okay, and then looking at the complex site, predominantly stable, but still a large percentage of time unstable. Okay, now for wind turbine development, you actually want stable, so flatter wind profile is good. It's good for the loading on the rotor and so forth. Okay. There we go. This is just a plot showing the power curve for the 2 megawatt wind turbine. It's pitch related, that's why we have a flat top part, 18 meter hub height, and a very small rotor, 75 meter rotor. Just a fictitious turbine. We use it to make comparison easier. Okay, right, just running through the pre-processing for the linearized code. So topographical data was imported with some grid data object, or graphic data imported with a line data object, and then the wind data was the wind turbine data was incorporated with the wind turbine object. And on your right hand side, you'll see some figures how it looks in the actual code. Here's some plots. Okay, where's the looking at the pre-processing setup for the nonlinear code. The topology and land cover data were included as one file format, imported in and managed in the terrain model. Then, unlike the linear code, for the nonlinear code you needed to generate a volume, a CFD mesh in effect. And for that, to have sensible results, you needed to perform some grid independence study, refining the mesh until you get a value of interest that is constant. So we did that, and we end up with the normal site having a mesh size of 1 million cells, and the complex site 4 million. Okay. So solving these two models as set up in the linearized code, there was, of course, the code requires no initialization, as within the nonlinear case. It solves the 2D and then extrapolates. There's a 2-step extrapolation process. Turbulence, it's not really calculated, but introduced via analytical means. Okay, and atmospheric stability was included as a heat flux. The wind resource map was extracted with a resource model, and the wind turbine yield we calculated with the park model. Okay. I need to step up a bit. Okay. Solving the non-linearized, or solving these models using the non-linearized code. Of course, there's some initial conditions you have to apply, but all this will be covered in the paper that's available on the web. Basically, it solves the 3D flow field, and using a two-equation Renaud average K-epsilon model. Okay, post-processing, this is just a table showing the tools used to extract the measures of comparison, the wind resource map, wind profiles, and energy yield. Okay, looking at two plots, that is the wind resource map, watts per square meter at a calculated height of 80 meters above ground level. From a first view, the patterns distributions look quite similar, and the value range of the watt per square meter is comparable. This is now for the simple site, and for complex site, there we go. Again, distributional coloring. You have your high wind speed conditions in areas where you will find them in both cases in a similar area, and the range of values are also comparable. Now this is a tricky one, comparing the two wind profiles at similar locations. Okay, there is some errors in here which needs further investigation. Okay, I'm not saying this is correct. If you can see, the blue line is showing the linear code prediction, and the green dotted line showing the non-linear. Okay, now, first of all, the shape of the thing shows that the stability conditions applied is not similar. One is stable, but the other one should be unstable. And also the offset, the shear velocity, that's also not correct. So this needs further investigation. Right, looking at the gross energy production predictions, ballpark, the difference is acceptable and is also in line with what has been published so far. And then discrepancies in the model results. Again, this is a work in progress. Nothing is final. Nothing is complete. We very much still will investigate all these errors and discrepancies shown. What we know that there's a small discrepancy between the two codes in a flat terrain. That is clear. And then the nonlinear model takes longer to compute and to get to an answer. There is still some uncertainty regarding what is put into the model, the atmospheric stability parameters, the shear velocity parameters. These all need to be investigated further. Okay, and also, especially on the nonlinear model side, because of the complex site is close to a mountain, there might be some boundary effects that's not incorporated in the model, but is present in the observed data. That need to be investigated as well. Okay. So right, so future work, hopefully to present it next year, WindAc, okay, the update on this. We need more mast, more measured data. Okay, a single mast is not optimal. Okay, and that increased your range of error. But that's adapt some reanalyzed data included into this model, perhaps. And David, I can maybe chat to you about that later. And then perhaps generate and start with generating a process where one could normalize the land cover data in South Africa and present a bit of a surface roughness map, perhaps, okay, and validate that. And like I mentioned, there's some obstacles perhaps on the boundaries of these models that need to be considered. And then, but in all, okay, this is pointing to a glimpse of the possible future, and that is how long are we still going to use models, okay, and with the new start of AI, and will there be a time in the future when one used live data, link it up to machine-learned model or algorithm, and adapt your input values with AI? Will that be a future? I don't know. Thanks for your time.
Thank you very much, Johan.
Thank you.
It's a very nice, quick run through the complexities of doing what we are really needing to do in terms of resource assessment for and using data and modeling in a very good and consistent way. Questions? There must be questions out there. Over here.
I know. Can you elaborate a little bit? You have MatMask data, but also then the one-dimensional and the CFD data. If you compare these, I assume 1D data should be the same than your MatMask data, but what's the difference between MatMask and CFD?
So we can go back to my slide. That wind profile slide is probably the best way of showing it. So in actual fact, we needed a baseline measured data to compare the performance of these two codes. Okay, and this is not here because we don't have an extra set of measured data, 1D observed data. So that is still missing in this graph. I hope I answer your question correctly.
But you mentioned MatMask, so you
Yes.
don't have these MatMask data to compare?
Yeah, the MatMask data. Okay, let's go back further. Okay. The MatMask data was used to generate the flow fields. It was not used to compare the wind profiles. So here you have, this is the location of the MatMask. The wind profiles was extracted at these red dots. There was no measurement here. There needs to be though.
Okay.
Okay.
And the other question.
Yes, sir.
In your when you showed your CFD grid, right,
Yep.
the mesh, there was it was not homogeneous. It was there was some direction that was finer and
Yeah, but
a coarse mesh. So is that related to the main wind velocity you have at the site?
so these positions fall within the refined areas in the grid.
So you correlated the fine mesh with the main wind velocities at the site?
Yeah. So the position of those points of data extraction was in the refined space. Yeah. Sorry, I should have.
Hi, sir. My name is
Yes.
Maggie. In one of your graphs, I saw that you presented the performance projection of the wind in future years to come. In years to come, let me say that. So I would like to know
Do you know
which
the
data.
slide number, perhaps?
Sorry?
Do you have a slide number, perhaps, or is it?
No, there is a graph that you've presented. It shows the projection of the wind in years to come, like the performance. Yeah, this one.
Okay.
So,
no, yeah.
yes, so I'd like to know what information did you collect to determine this?
Okay. Yes, it's not a projection of what's going to happen in the years to come. This is just typically the lifespan of a typical wind project.
Okay.
Okay, which is 20 years.
Okay.
And this is the profit generated by such a wind project. Okay. And the blue line is the energy yield as base case, and then the orange line is just the energy yield plus an addition due to high accuracies in modeling prior to pre-construction.
Okay.
So, of course, this is a cumulative effect between those two differences that will yield increase in profit.
Okay. Thank you so much.
Thank you for your question.
One last question over here. Mike is coming. Ah, well, okay.
Johan, I would like to know this part of modeling methodology that you use, which are linear or non-linear. I would like to know which kind of design approach do you use to model your code?
To model?
To model your code, your benchmark code. Which kind of design approach?
Design approach.
Yes.
In wind farm design?
No, which kind of design approach? Because you say your system was linear and non-linear.
Yes.
Which kind of design approach do you use to make it linear or non-linear?
So, so these codes basically, to some extent are different flavors of the Navier-Stokes equation. They have to some extent some Navier-Stokes equations in them. Okay, some of them are linearized versions of the Navier-Stokes, or rely on that to some extent, and the others are full Navier-Stokes, full nonlinear equations. I didn't tweak any models whatsoever. It was just stock standard what's available on the market.
The last one.
So I hope I answered your question. Thank you.
Hi, thank you. My name is Emily. I wanted to ask you, you gave us this figure at the beginning of 91% of the energy being produced, the prediction from the model was being produced. So for the models that you have worked on, did you see an increase in your prediction?
No, I haven't considered it yet. No. Where are we? Is it back, I suppose? Sorry. I'm going forward now. Sorry, I'm just going to quickly go to that slide. Is this the graph you were referring to? Okay, so it's what this graph show. Okay, it's not only the modeling implications or inaccuracy in modeling that's yielding this underperformance of wind farms, but it's a number of factors. It's the technology, it's the accuracy of wind power curves for wind turbines, it's perhaps the placement that this was not accurately because of, as you know, I mean, what you modeled and what's applied is not necessarily the same thing. Okay, sometimes you need to shift turbines in a site due to environmental issues of some sort. So this is all those factors included. What percentage is known or contributes, what percentage modeling contributes to this, it's hard to see from this graph, and I don't know, frankly.
So I suppose I'm asking, for the models that you have worked on, that you've taken us through, were you able to obtain actual production figures and compare that to the models that you worked on?
These models were applied in simulating the pre-construction yield of these wind farms. So they were already embedded in this, okay. And whether I would improve it, I don't know. I don't think so.
And Johan, you should also maybe, am I right in also assuming that, I mean, there's a development over time, there's a trend in the quality of what this is happening.
Yeah, so
you're noticing here that Johan is mentioning this study was in 2011, right?
Yeah. So yeah, I think the norm now is 97%. Okay. I have a paper on that. I can mail it to you.
And I think I'll refer you to the paper for or direct discussions later because time is flying and we need to go to the next speaker. Thank you, Johan, and let's.
Work is part of the Wind Atlas of South Africa project, and I explain a little bit how did we come up with this topic. It's actually very much related to this conference. So during the phase 1 and phase 2 of the WASA project, we have run mesoscale simulations to determine the wind climatology over South Africa. I'll explain a little more about some of these terms later on in more detail, so don't be afraid. I know some of you are familiar with these terms, some of you might not. I'll talk a little bit more later on. So we have used this data to make downscalings for South Africa, and by the way, there is a banner right out front that you want to, if you want to take a look at. These new results are right off the press. Maps were done a couple weeks ago, so they are brand new. And then now it's covering a much larger area of South Africa. You can see here on the phase 1, we were mostly focusing in the most coastal regions, and in the second phase of WASA, and this map actually covers all of South Africa. So there are places that might be new to you that were not defined before. What happened was we were here at this conference last year, and actually 2 studies were presented that were based essentially on very much the same simulations that I perform at DTU, and the data went into 2 different maps, and they seem to be very different. And I will show you that. Okay, so this is the WASA map. Maybe you're familiar with it, you've seen it before. This is the power flux for these two most coastal areas, and this was produced in 2014. And then at the conference last year, there was a second map that was presented, and it had, this is a different parameter, but people were a little confused and saying, well, this has a lot of blue areas here, how come this has a lot of white and red areas? We're confused here. Why is it that these two things show very different things? So that is the purpose of my presentation here, is to try to clarify why these things are different and what are these things be used for different things. So I will be very didactical and try to go through all the steps that go into making one of these maps and making one of these maps and compare and hopefully convince you that no, they are consistent with each other, but they are different products. So essentially, while the studies were using the same data, it seemed apparently that they were showing different resources for South Africa. So let's go through a little tutorial of wind power basics. So you've seen before in presentations, you have some measurements, and for the WASA sites, we have 14 masts. Some of them have been there for quite a long time. So you take the measurements from here, and you will get a time series of wind speed and wind direction, and Stefan was very good at introducing some of the data that comes from here. From this data, you get a distribution, which is what we call wind climate. That's very much jargon among us resource assessment people. We talk about this all the time. But one basic thing here is that this is an intrinsic characteristic of the site. This is a place, you know, you go up on top of Table Mountain, how windy is on top of Table Mountain. It's a characteristic of the site, of the wind speed that goes into the place, right? And, oops, I went too far here. Okay, so from this distribution, you can compute a mean wind speed, and it's just a temporal mean of all the speeds that you have. You can do it in directions, you can do it any way you want. And then you also have the power density, and that one is a function of the cube of the wind speed, and it also depends on the air density. So if you are in a site higher up, your air is less dense, so the wind turbines actually generate less power, and you should probably take this into account. Most of the time, it's a good approximation to actually make an average density for the site instead of having to compute the density at every time step. So these are still characteristics of the site. Okay? Now, when you place a turbine at a particular site, this is what you could. This is the potential of the site. So this is the gray part here. Now there is only a usable part of that could be extracted by a wind turbine. And then the red curve actually shows you for a given wind turbine, this is how much this one could extract at a particular site. And you can see that they are essentially quite different. And the resulting is that if you want to determine what is the actual production or yield in a particular site, you have to multiply this wind climate by this power curve. And this will give you the energy output. So this is another measure. But here you see you depend on two things. You depend both on your wind climate at the site, and you depend on the turbine and the characteristic of the turbine. So now we're talking about a much more derived quantity, okay? And I'll give you an example here. This is the Vestas turbine, and actually the Vestas V90 turbine comes in two flavors. You can get this one with a 2 megawatt turbine generator or a 3 megawatt. The rest of the turbine is exactly the same. The height, the length of the blades, everything else is the same. You only have two different generators. And by the way, the price of the turbine is actually very comparable. You will pay a little more for a 3 megawatts instead of a 2 megawatts, but most of the price of the turbine is actually all the other things that come along with it. But you can see the two turbines have a different power curve. And if you take a look, this is one of the sites, is actually one of the WASA sites. If you take the wind climate, you can see that the energy yield is quite different. You get 6.8 with the 2 megawatt and 7.8 with the 3 gigawatts. But now there is something else that's called the capacity factor. And what this tells you is the percentage of the time that your turbine is running at full capacity. And it turns out that for the 2 megawatts, you actually 39% of the time is that case. But for the higher 3 megawatt, it is only 30%, right? But this one is actually producing more energy, but for essentially a less time, okay? So you can see that you can get quite different results depending on which turbine you select. You still have the same climate at the particular site, but the two turbines will actually perform quite different, and you can. It depends on your site. You will make an assessment of what kind of turbine you will place in that particular site to make the best out of you. Of course, none of this is taking into account what's been spoken before, which is the price of your turbine. And if you want to make money out of your investment, you need to make this whole assessment. But let's look at some maps. This was the objective of the presentation. But I think I have defined all the factors that we talked about until now. For these wind atlases, and when I'm talking about maps here, the slides before were based on measurements from a site, and actually is WM14. And the maps that I'll show you later on are actually produced by simulations. They have been initially verified, but all the data I'll show you from now on comes from a model. But how do we get these models? Well, what we do is we take the reanalysis, which was very much described before. So we take reanalysis in a global model. We run a mesoscale model to do a regional map. And in this case, for example, it's called WRF. Then we take a particular site and we run a microscale model. And then also we had a very good introduction before I came. And in this case, it's WASP, it's a linear model. And you can see this downscaling here was done at a 5 by 5 kilometers, and the microscale modeling here, based on this data, was done at 250 meters by 250 meters. So essentially, what Stefan was showing you before for one site was done for, I don't know, 200 million grid points that cover all South Africa. But let's go to some maps. Ding. Try again. Ah, there we go. Okay, so this is a picture of what WM14 looks like, and you can see it's located here. So it has quite a complex topography. So let's look at the yield for this site. If I can go, okay. So you can see the same kind of relationship. So this is for the 2 megawatt turbine on your right or your left, and the 3 megawatt on the other side. And you can see that actually if you take into account just the production, you see much more red colors on this end than you see on this case. Now, if instead of the energy yield, you choose to plot the capacity factor, now you can see that actually for this, for the 2 megawatt turbine, you actually have higher capacity factors that you do on the right for your 3 megawatt turbine, right? So things kind of reverse depending on the technology that you're using, right? But actually, all this is very nice, and so you need to know what is it that you're looking at. Essentially, this is the main idea here. Are you looking at a quantity that it's part of the atmosphere, which is the wind speed or the power flux, or are you looking at a map that refers to the characteristic of a given turbine, which I can change one or another, and then you will see different colors on this plot, right? But there is one more factor to speak of here, which is that, that you have to be very careful, on your resolution of your maps, and I'm almost finished here. So this is the same site that we were talking about before, and in this case, what we show is the mesoscale prediction coming out of your mesoscale model, overlay over your mesoscale topography. And this has a special meaning for somebody here in this audience. Now, actually, if I plot these mesoscale predictions over the topography of the microscale, so this is the map that you look at right at the beginning, you can see that they are actually inconsistent. If you try to understand these blocks here, they really physically don't make sense. So what you need is actually to make a microscale prediction for each of these sites. And you can see that now things make sense. The red areas are on the top of the hills where you will expect them, and where you will place a turbine if you were making a wind farm project. But let's compare these two, and this is a summary. So actually, even though you can see that the average of the grid is more or less similar, you have about 6.7 and 7 AAP for these two grids, and this is the average over all the points on the grid. Now that you come to the ranges, you can see that in this plot you will have sites that will have much more energy than the others. And so the resolution is very important when you look at this. And if you were to make a calculation just based on this, you will probably underestimate the amount of power that this site could provide you. And that is the main question, the main issue here. And so I'll go to my conclusions. I don't know how we're doing now, Carson. But anyway, the intrinsic characteristic of the atmosphere, the mean wind speed and the mean power density is just a function of the atmosphere and the site that you are. The power density, you have to be a little careful about the power density maps because they integrate all the way to infinity of the wind power, but the wind farm will actually shut down often if you are above 25 meters per second. So you have to be a little bit careful for this. The air density matters, so you should probably take that into account. But then other quantities depend on the turbine, the technology that you're using. So you have to be careful not to confuse these with these. They are different things. And that's probably the explanation of the two maps that we were looking at the beginning, why they look so different. And then often the mean of your mesoscale is not the average of the wind speed of the whole grid. That is not the way this works at all. And the wind turbines don't turn with that mean wind speed of a box. They turn with whatever you place them in that box, and that's a very important concept in the resolution. And we've done some tests. I didn't show them here, but you need to go to about 100-meter resolution before it actually looks quite realistic. And of course, all these last plots, they're models, they're not reality. Remember about this. We got uncertainties propagating everywhere here. Right? But it's an illustration of where you can get through, and through validation, you gain more confidence on these projections. And I'm sorry, maybe went a little too far.
Thank you very much, Sandra, and you were very fine on time. Okay. So questions? Any questions? There are a couple over here.
Oh, all clear.
Yeah.
My God.
Hello, ma'am.
Yes.
I wanted to ask, between wind density and wind power, which one is more important for you to be able to have a sustainable wind farm in a correct geographical farm?
it was a little not very loud, but you're asking about the difference in this case between density, how much that could affect a prediction. Is that your question?
Yes.
It depends on the altitude. Density decreases in the atmosphere with height. So it's much more dense here in Cape Town, that we are near the beach at sea level, that if you go to Lesotho in some of the higher mountains. And I think within South Africa, we say maybe 20% variation or something of that sort, that it should probably be taken into account. And also these power curves that I was mentioning before, they are given for different densities, and you have to be careful when you apply them to your turbine to use the right power curve for the right density. Because the test that determines that power curve is done at a particular site that has a particular density. I hope I answered it.
Yes, thank you.
Please go ahead.
Hi, good morning, Richard Worthington. With the second set of data that was released by CSIR, the most recent that you referred to, there's a map of the wind capacity factor nationwide. Is that corrected for air density, or is that a calculation before that is taken into account?
I'm not sure. Maybe Tobias can answer that question. If it was corrected for density.
Yes.
It was? Okay. Yeah. But I think the ones we have are not.
The speed values are not.
Speed values are speed values, but the power density. Don't think so. Is it? Yes. Is it? Okay. Good. Good to know.
Hello. So I just want to find out on your side, have you guys actually tried to investigate how the installations of wind turbine in the Cape might have an impact on the tourism industry? That is my first question. And the other question, in one of your slides, I think you show, I think it's something like slide 8, you show different capacity factors for 2 megawatts as well as the 3 megawatt. Do you have some information about how the capital costs as well as the fixed O&M costs for those plants compare, so at least we can work out the LCOE for those?
Yeah, sorry, you're asking the wrong person for both questions. I'm a weather modeler, so I really don't know about it. I mean, to me, going and looking at wind turbine is tourism. I find them beautiful. So that's all I can say. And actually, in Denmark, we have made a visitor center in one of where the very, very tall, enormous turbines are. And it attracts a lot of people that come and visit them. So it's a nice thing, but yeah. Maybe there are other presentations later in the week in that kind of subject. I believe so. Yes.
Can I have a final question, please?
Andrea, I would like to ask, which software do you use for your meso-skid and macro-skid? I mean, from the global to meso, macro-skid, which software do you use? Is online or maybe is not online? And also, I would like to ask, my second question is about energy crisis, water crisis, climate change. As on the beginning of your presentation, you show us two maps. Those are different for 2 different years. Do you think after 100 years or 200 years, the wind speed average will be the same also, or maybe wind average speed will decrease?
Okay, let me take the first question was mentioned already. The mesoscale model was WRF, and that's WRF version 3.6.1. And actually, there will be a report will be published on the WASA website about all the characteristics of the models used in these maps. So you just need to wait for us a couple of weeks. There will be a full report describing all the methodologies used here. On the issue of climate change, there is actually a lot of research being carried out right now, and actually the group from University Cape Town has done some research on that. So it's not, at least for South Africa, it's not my particular knowledge right now. But yes, the atmosphere is changing and the flow will probably change. Now, how does it impact the capacity of extracting energy? It's another question. We need young people like you to take that kind of research and define these things. All right?
Thank you, Andrea.
Yeah, I'm Celeste Renaud. I'm from the University of Cape Town. This morning I'm going to be presenting my honors project, so don't expect anything groundbreaking. But yeah, hopefully it gives a glimpse into how wind research is really developing as a popular topic at many universities in South Africa. My supervisor is Dr. Chris Leonard, and the title of this project is Wind Characteristics of the Northern Cape and Relation to Prevailing Synoptic States, a contribution to the WASA Phase II project. So the aim of this is to link wind speeds and prevailing synoptic conditions, as we believe it might be a valuable contribution to wind power for the wind power assessment process. So let's see if I have strong fingers. There we go. So as mentioned by Dr. Hahmann, that figure is the WASA Phase I map. It is the most comprehensive map to date. However, and this is the motivation, or was the motivation for our research at the beginning of the year, many inland areas are yet to be mapped by the WASA project. WASA Phase III plans to expand comprehensively into the Northern Cape interior, and this project was sort of a preliminary examination, rough examination of the wind resource of this area. The motivation for this was that previous wind resource assessments prior to these recent maps, as shown in Dr. Hahmann's work, suggest that inland wind speeds are generally quite low. However, these assessments have been labeled as unreliable and very much inconclusive. And furthermore, research regarding the relationship between surface wind speed and synoptic condition is lacking in South Africa, which is a gap that our research aims to address. This led to the aim for our study, which was to perform a preliminary examination of the Northern Cape interior wind resource as a contribution to the WASA Phase III project, which is actually being launched on the 17th of November, so very soon, and to investigate the synoptic drivers behind these characteristics. The objectives set to achieve this aim were to investigate wind speed and characteristics of the Northern Cape interior and to examine typical synoptic states over South Africa and their relation to surface wind speed in this area. In terms of our methodology, we produced a mean annual surface wind speed map using the WARF model, which has been mentioned by Dr. Hahmann. This was a mesoscale map. We secondly extracted wind speeds for 2 locations within the mapped area. These were Uppington in the north of the province and De Aar in the south, using the WARF data set of simulated wind speeds. Each time series of wind was analyzed for a seasonal wind cycle. Third, we produced a self-organizing map of pressure data using the ERA interim reanalysis data set, which has been described by David Pullen earlier on. And yes, the bottom figure is an example of a SOM which depicts 12 typical synoptic states or prevailing pressure states over South Africa. Each day from the data set maps to a particular node in the SOM, and that produces a daily node number series. So this daily node number series was matched with our daily wind speed data, and the average wind speed and range was calculated for each node at each location. Finally, we compared surface wind speeds of D'Ar and Uppington to those of 4 WASA Phase I sites, which have been validated against observational data. This was our mean annual wind speed map that was produced. Large areas of 4 to 5.5 meters per second exist, as shown by the widespread light blue area. Low wind speed areas are indicated by the dark blue patches, which can be seen mainly in the central and northern parts of the province. These have wind speeds of less than 4 meters per second. Uppington is situated near one of these areas. And high wind speed areas are indicated by green, yellow, and orange. And these can be seen mainly in the southern parts of the province, particularly along the southern border. And also a little patch in the northeast. D'Ar is situated near one of these areas. These were the seasonal wind cycles that we identified. Both locations show relatively low mid to late summer wind speeds, which build to a peak in late winter, barring a dip in wind speed for D'Ar during winter. The end of the year shows slightly different characteristics for each location, with D'Ar sustaining relatively high wind speeds in early summer, and Uppington showing quite a drastic drop from late winter into spring and early summer months. D'Ar wind speeds were generally 1 meters per second, or on average 1 meters per second higher than those in Uppington. Oh, sorry, one back. Now it's doing overtime. There we go. These were our results for our synoptic states and their frequency. So on the left are your 12 typical pressure states over South Africa. And on the right is the frequency of each of these states for the 2005 to 2013 period. We found that in summer, nodes 8 and nodes 12 were the most dominant. Node 8 represents a heat low, which is basically a low pressure system situated over the interior of the country. And node 12 represents the development of a tropical temperate trough, which is when a low pressure system in the south becomes linked with a low pressure system in the north, resulting in a large scale transfer of heat, moisture, and momentum. Previous literature suggests that these are distinctly a summer phenomenon. We found that there was a definite peak of these phenomena in early summer, but that they also were experienced all year round, which was quite interesting. Oops. In winter, nodes 5 and nodes 10 were most dominant. Node 5 represents a continental high, which is when a high pressure system becomes situated over the central interior of the country, often resulting in the subsidence of air. And node 10 represents a cold front, which many of us from the Cape are very familiar with. Well, not so familiar with recently. And then, so we matched the daily synoptic data with the daily wind speed data and found that for D'Ar, node 12, which was a tropical temperate trough, was associated with the highest wind speeds, and continental highs were associated with the lowest wind speeds. In Uppington, we found that cold fronts are associated with the highest wind speeds, and heat lows are associated with the lowest wind speeds. We also found that some synoptic states were associated with differential wind speed outcomes in each location, possibly due to geographical location of each of these areas. So this led us to do a comparison of 4 main synoptic states and their wind speed outcomes for D'Ar and Uppington. We found that winter phenomena, such as continental highs and cold fronts, were generally associated with lower wind speeds in D'Ar than in Uppington. This was particularly surprising for cold fronts because we expected regions or more southern regions of the province to be more influenced by cold fronts which originate in the south than those in the north. So this suggests that cold fronts may have more far-reaching effects on wind speed in South Africa than we had anticipated. In terms of the summer phenomena, generally they were associated with much higher wind speeds in Dar than in Uppington. Previous literature suggests that Dar wind gusts are heavily influenced by thunderstorm gust fronts, which are more often than not associated with heat low and tropical temperate trough conditions in this particular area, and could explain the relatively higher wind speeds in this town. Finally, we did a comparison of the wind speeds, the surface wind speeds at Dar and Uppington with 4 WASA Phase I measurement sites that were closest to the Northern Cape interior. We found that Dar compared very well to the wind speeds of Calvinia, which is WASA Mars Station number 2. Calvinia is situated very near to the Louriesfontein and Korbab wind farms, and that area has been identified as having an excellent wind resource, which was quite interesting. There we go. In terms of wind power investment, our map is obviously way too coarse for any site selection and microscale assessments. Those were mentioned by Dr. Hahmann as well, would be required for this. However, we did establish an important link between surface wind speed and synoptic condition. And this leads us to think that future changes in synoptic patterns could have serious implications for the wind resource of not only the Northern Cape interior, but South Africa as a whole. Frontal systems, for example, are projected to move further southwards in future, which could mean less interaction with inland pressure systems to set up strong pressure gradients, such as cold fronts. It could also mean less tropical and mid-latitude interaction, which could result in tropical temperate trough circulations. Both of these have proven to be high wind producing mechanisms in some areas of the Northern Cape interior. Therefore, a decline in the frequency of these could mean a decrease in surface wind speed and therefore less wind available for wind energy. In addition, heat lows are expected to intensify in future, which could mean more intense thunderstorms and thunderstorm gust fronts, which could mean higher but more variable wind speeds in places like Dar. We therefore argue that synoptic information should be an important consideration when selecting locations for wind power investment. In conclusion, we found that the Northern Cape interior has higher wind speeds than previous studies suggests, those being those prior to the maps that have been produced in the recent year, particularly in the south of the province. And we also established an important link between surface wind speed and synoptic state. The recommendations for further research: we would obviously need a validation of the wind speed map and an investigation of more sites. Both of these will be done in the WASA Phase III project. An extreme wind atlas, which will investigate things like thunderstorm gust fronts, strong winds, and hourly variability of wind, which we have not explored in our project, will also be done in WASA Phase III. But our main recommendation from this study is that further research should focus on the future of synoptic trends to incorporate into the wind power assessment process, as we think it could be a valuable contribution. And that's it from me. Thank you.
Thank you very much, Celeste. And questions? Very interesting to see how you are looking at weather and climate change effects and what that can bring to understanding wind resources is really important. Questions?
So Celeste.
Hi there.
Thank you for the nice presentation. Just one question. Synoptic, maps, and icing. Is there a link?
And sorry?
Icing.
Icing.
Yeah. Do you think there's probable icing events in the Northern Cape?
Icing in terms of like ice being?
At a, say, 100-meter level or something like that, above ground level.
Oh, potentially. Can I call my supervisor?
Please.
Thank you. Your recommendation of incorporating it into future yield assessments, what sort of time scales, well, you mentioned the synoptic patterns are expected to change. What sort of time scales could we expect those to happen on?
So, I mean, I think that's the big question, is what sort of timescale is going to be most urgent for wind farm investors? What are they going to be thinking about? Is it going to be the 20-year span of, for example, a wind farm? Is it going to be looking at future like wind farm investment as a whole? I would presume that it would be for the lifespan of the wind farm. And yeah, that would be my presumption. So however long that may be, and however long that may develop to be in future.
Thank you. Is there one final?
Which node are we today?
Today?
Yes.
Sure. Hopefully node 9.
No, your synoptic patterns.
I think today, well, we got a bit of rain, but
It was a cutoff low.
yeah, it was probably a cutoff low. So
Sorry,
I'm
I
not
put you
sure.
on the spot.
probably something to do with
Meteorology or blood.
yeah, bit of a mix maybe.
Thanks a lot, Celeste, and thank you to all the speakers.